Hello students! So this video will be shorter than a lot of the previous ones because I have a very specific goal. I just want to prove that if a function is continuous on a closed bounded interval, then that function is uniformly continuous. That is, I want to prove this theorem, theorem 3.8.9. And maybe I'll start by trying to convince you of why this theorem should be believable by considering the two counterexamples that we have right now, the two examples of continuous but not uniformly continuous functions. So one of them was the function f from 0 to infinity to r given by f of x equals 1 over x. So let's go ahead and look at that. There it is. And if you notice, the place where uniform continuity failed was close to 0. Right, the points we found, that the inputs we found, which were close to each other, but didn't have close outputs, well, a bunch of inputs that got close to 0. Right? The inputs that get close to 0 have outputs that get very far apart from each other. So if we just stay away from 0, if, say, we restrict the domain to be 1 to, I don't know, 5, then yeah, it looks like on that interval, if you take any two inputs that are close to each other, the outputs sure seem to be uniformly close to each other as well. And in fact, we saw exactly that happen when we proved this claim. So it's believable. The failure of uniform continuity appears to happen at just like a few bad points. So one way of avoiding those few bad points which aren't in the domain is restricting to a closed bounded interval, because that you can't get close to those bad points. They won't be limit points. So let's prove it. Let's suppose that a is less than b and f from a to b to r is a continuous function. I need to show that f is uniformly continuous. Let's suppose, for the sake of contradiction, that f is not uniformly continuous. And let's write down what that means. So f is not uniformly continuous means, so you can safely fast forward through this if you feel very comfortable with your negation of formal expressions. But here we go, let's write it out. So not f is uniformly continuous means not, now the definition of uniform continuity, not for all epsilon greater than 0, there exists a delta greater than 0 such that for all x and a, I think are the letters I will use in the proof, in the domain, actually x better be x and p, because a has a job, doesn't it? For all x and p in a comma b, if absolute value of x minus a is less than delta, then absolute value of f of x minus f of a is less than epsilon. So let's negate that expression by doing what we know how to do. The universal quantifier will become existential. There exists epsilon bigger than 0 such that for every delta greater than 0, there exists some points x and p in a, b, such that absolute value of x minus a less than delta and not the conclusion. Absolute value of f of x minus f of a greater than or equal to epsilon. Nice, so now let's just write that down in the space for it. Suppose, for the sake of contradiction, f is not uniformly continuous, then, well, what do we know? We know that for all epsilon, we know that there exists an epsilon greater than 0, such that for every delta greater than 0, there exists some x and p in a comma b, such that absolute value of x minus p is less than delta, and absolute value f of x minus f of p greater than or equal to epsilon. So here's how the proof is going to go from here. I have this sequential reformulation of continuity. I'm going to take advantage of that. This isn't by any means the only way to come up with this proof, but this is the proof that I'll use. So how can I get a sequence worth of information here? So this epsilon is just some fixed constant. I don't know what it is, but it doesn't depend on anything. It will just, I'll call it epsilon, it'll be a number. I know that something is true for every delta bigger than 0. For every natural number n, I can come up with a choice of delta. I'll call it delta n. And these delta n's can get increasingly small. Then for each of those delta n's, there will be an x sub n and a p sub n. I may as well encode the fact that they depend on the choice of p, such that those two conclusions happen. Sorry, these two conclusions happen. So let's put pencil to paper and write that. So we'll construct a sequence that sees this failure of uniform continuity. Consider that fixed epsilon from above. Let's let delta n be your favorite choice of deltas which are all positive and yet converge to 0. So, I don't know, standard one is 1 over n. You could use 1 over 2 to the n. It won't make a difference. By the failure of uniform continuity, that is item 3.20 above, I see that there exists some p sub n and x sub n such that this happens. Such that absolute value of x sub n minus p sub n is less than delta sub n, and absolute value of f of x sub n minus f of p sub n is greater than or equal to epsilon. And remember, that epsilon is a fixed constant. That epsilon isn't something that's getting arbitrarily small. As our first step, let's take advantage of the fact that we know that these two sequences, and maybe I'll focus on p sub n. There'll be some inconsistency in some of the next couple lines, but those will be fixed hopefully before you see the physical notes online. So I see two sequences, x sub n and p sub n. Let's explain why p sub n is bounded. Well, you already know why p sub n is bounded. For every n, p sub n is in the closed bounded interval ab. So that means a is less than or equal to p sub n, b is greater than or equal to p sub n, a is a lower bound, b is an upper bound. Let's just put that into WADs. Let's prove that a and b are bounds. So let's do that. Let's consider any n in n. We need to show why a is less than or equal to p sub n is less than or equal to b. And, well, what do I know about the sequence p sub n? I know that p sub n, well, I know lots of things, but I know in particular that it is in a comma b, by this line. Since p sub n is in a comma b, a is less than or equal to p sub n is less than or equal to b. So we've now proved that for every natural number n, because we considered any natural number n, that a is less than or equal to p sub n is less than or equal to b. A and b are bounds on p sub n. In particular, p sub n is bounded. So the Bolzano-Weierstrass theorem says something about any bounded sequence, and I'll switch from xn to p sub n. Like, xn and pn are really supersymmetric. You could interchange them and the same proof would work, but I'll stick with p sub n. So the Bolzano-Weierstrass theorem says that p sub n has a convergent subsequence. P sub n has a convergent subsequence. Well, if it has a convergent subsequence, let's just give it a name. Let's let p sub n sub k be a convergent subsequence of p sub n, and let's let p be its limit. Let's explain why p is in the closed interval from a to b. Well, let's do that. What do I know about p sub n? I know that for every n in n, p sub n is in the closed bounded is in ab. But every n sub k is a natural number. So let's focus on p sub n sub k. For every k in n, p sub n sub k is in a comma b. So A is less than or equal to P sub n sub k is less than or equal to B. Ah, so that's an inequality that's satisfied for every term in that convergent sequence P sub n sub k. Taking the limit, I see that A is less than or equal to P is less than or equal to B. So P is in A comma B. And what's the point? Why should I care about that? Well, I should care about that because f is continuous on the whole closed-bounded interval a comma b by assumption. So since p is in the closed-bounded interval a comma b, f is continuous at that particular input. But before that, let's think about x sub n sub k. So what do I know right now? I know this, and I know P sub n converges to P. But let's look at x sub n sub k. Let's see. For all k in n, I know that x sub n sub k minus P sub n sub k is less than delta n. So minus, delta n sub k. So minus delta sub n sub k is less than or equal to x sub n sub k minus P sub n sub k is less than or equal to delta sub n sub k. Oh, but check it out. That goes to 0 because delta n goes to 0. That goes to 0 because delta n goes to 0. So, by the squeeze theorem, x sub n sub k minus P sub n sub k must converge to 0. Nice. Alright, well, let's see what we know. I know that P sub n sub k converges to P. I know that x sub n sub k minus P sub n sub k converges to 0. And we've proven this in the past. If x sub n sub k minus P sub n sub k converges to 0, and P sub n sub k converges to P, it must be that x sub n sub k also converges to P. And that's why it doesn't matter if you thought about the x's or the p's, you got the same information out of both of them. So let's look at this. F is continuous on AB by assumption, and P is in the closed bounded interval a comma b, and F is continuous at P. I know that x sub n sub k converges to P. P sub n sub k converges to P. So I have the sequential continuity trick. This must mean that f of x sub n sub k converges to f of the limit of x sub n sub k, f of P. Similarly, f of P sub n sub k must also converge to f of P. Oh wait, so if f of x sub n sub k converges to f of P and f of P sub n sub k converges to f of P, they both have the same limit, then the limit of the absolute value of the difference is 0. Wait, so let's see, that's probably, that seems suspect, because let's look at this. So I have this result. Sorry, this result, the limit there is important. So that sequence goes to 0. But for every n, f of x sub n and f of P sub n are not close to each other. But they're getting close to the same thing because of this. Alright, let's get that contradiction then. So, by 3.2.1, this, I know that for every k in the natural numbers, the absolute value of f of x sub n sub k minus f of P sub n sub k is greater than or equal to epsilon. Right, because I know that's true for every f of x sub n minus f of P sub n. So in particular, it's true for every x sub n sub k minus P sub n sub k. Wait, but if that's true, I know that the limit of the absolute value of that difference exists, so I can use limit laws to conclude that this difference is greater than or equal to epsilon, which in turn is greater than 0. But that's a contradiction. I know that the limit is equal to 0, and I know that the limit is bigger than 0. So we reached a contradiction, so the thing that we assume for the sake of contradiction must be false, so it must be that f is uniformly continuous, as we claimed. So the next video I'm going to post will go through a very similar proof, But instead of thinking about just closed bounded intervals, I'll walk over any compact set. And really, the hypotheses of what a compact set means are exactly the hypotheses that we really used in this proof. So the proof of this next theorem will be a little bit easier if you watched the video and read the lecture or read the notes about compact sets. Great, well, I'll see you in a moment.